What if the stars we see are only echoes from a universe that has already ended? This documentary explores cosmic light delay, heat death, false vacuum decay, and the terrifying idea that reality may already be over. We just don't know it yet. In this video, we're going to explore what if the universe is already dead. And by the end, you'll uncover mind-bending ideas from cosmology and physics that challenge how we think about time and reality and the universe. If you're a space and science enthusiast like me, this channel is definitely made for you. Let's get started. Close your eyes for a moment and picture yourself standing outside on a clear night, far away from city lights. Above you stretches the vast canopy of stars, thousands of tiny lights piercing the darkness. You have looked at this sight countless times in your life. It feels immediate, feels present, feels like you are seeing the universe as it exists right now, in this very moment. But what if I told you that everything you are seeing is a lie? Not a deliberate deception, but something far stranger. What if every single star you are looking at is showing you the past, not the present? What if some of those stars died centuries ago, but their light is still traveling through space to reach your eyes? What if you are not looking at the universe as it is, but as it was? Now, take this thought one step further into truly disturbing territory. What if the entire universe has already ended? What if somewhere out in the vast darkness of space, reality itself has been destroyed, rewritten, or simply stopped existing? What if you are living in the afterglow of a dead universe, watching old recordings of light from stars and galaxies that are no longer there? This is not science fiction. This is a real possibility that emerges from our understanding of how light works, how the universe expands, and how information travels across cosmic distances. For the next few hours, we are going to explore this deeply unsettling idea. We will examine how the speed of light creates a fundamental barrier between us and knowing what is happening right now in distant space. We will look at the ways the universe could die, suddenly or slowly, and we will confront the terrifying truth that if the universe is dead, we might not know until it's far too late to do anything about it. The journey we are about to take will change how you see the night sky forever. The speed limit of reality. To understand how we could be living in a dead universe without knowing it, we first need to understand something fundamental about light. Light is the universe's messenger. It is how information travels from distant places to reach your eyes. When you look at something, you are not directly perceiving it. Instead, light bounces off that object, travels through space, enters your eye, and your brain interprets the signal. This happens so fast in everyday life that it feels instant. But light is not infinitely fast. It has a speed limit. Light travels at approximately 300,000 kilometers per second. That sounds incredibly fast, and by human standards, it is. If light could travel around the Earth's equator, it would circle the planet more than 7 times in a single second. But the universe is so vast that even this tremendous speed becomes painfully slow when dealing with cosmic distances. Let me give you an example that will help you understand what this means. The Sun, our closest star, sits about 150 million kilometers away from Earth. When light leaves the surface of the Sun, it takes 8 minutes and 20 seconds to cross that distance and reach your eyes. This means that when you look at the Sun, you are not seeing it as it exists right now. You are seeing it as it existed 8 minutes ago. The Sun could have vanished 8 minutes ago, and you would still see it shining in the sky for another few seconds before it finally disappeared from view. Think about what this means. If the Sun exploded right now at this very moment, you would have no idea. You would continue seeing sunlight for 8 more minutes. Birds would keep singing. People would keep going about their day. And then, without warning, the sky would go dark. But that darkness would not be happening in real time either. It would be the information about the Sun's destruction finally reaching Earth after traveling for 8 minutes through empty space. This delay gets worse the farther away you look. The nearest star system beyond our Sun is Alpha Centauri, sitting about 4 light-years away. A light-year is the distance light travels in 1 year, which equals about 9 trillion kilometers. When you look at Alpha Centauri, you are seeing light that left that star 4 years ago. You are looking 4 years into the past. If aliens living near Alpha Centauri destroyed their planet 4 years ago, we would not see it happen until today. The North Star, Polaris, which humans have used for navigation for thousands of years, sits 433 light-years away. The light you see from Polaris tonight left that star in the year 1592, when Shakespeare was 28 years old and had not yet written most of his famous plays. You are looking at a star as it existed in the Elizabethan era. Let that sink in deeply. When you look up at the night sky, you are not seeing the present. You are seeing a museum of cosmic history. Every star is showing you a different moment in time. Some show you decades ago. Some show you centuries ago. Some show you millions of years ago. The universe you observe is not synchronized. It is a patchwork of different eras, all appearing to exist simultaneously. Now imagine receiving letters from friends who live in different countries. One friend lives nearby, so their letter arrives in 2 days. Another friend lives across an ocean, so their letter takes 2 weeks. A third friend lives somewhere even more remote, so their letter takes 2 months. When all 3 letters arrive, you read about what your friends were doing, but each letter tells you about a different point in time. The nearby friend's letter is nearly current. The distant friend's letter is describing events from 2 months ago. You cannot know what any of your friends are doing right now. You only know what they were doing when they wrote their letters. This is exactly how observing the universe works. Light is the letter. Stars and galaxies are your friends, and the speed of light is the postal service. You can only read the letters that have already arrived, which means you can only see the past. The present state of distant objects is completely hidden from you. This is not a limitation of our telescopes or technology. This is a fundamental feature of how reality works. Information cannot travel faster than light. This is one of the most important discoveries of modern physics made by Albert Einstein over a century ago. The speed of light is not just the speed that light happens to travel at. It is the maximum speed at which any information, any influence, any cause and effect can propagate through the universe. You cannot send a signal faster than light. You cannot observe something faster than light can travel from it to you. This creates a barrier between you and knowing what is happening right now anywhere except in your immediate vicinity. Even in your own room, the light from objects takes a tiny fraction of a second to reach your eyes, meaning you are technically seeing everything in the very recent past. But for cosmic distances, this delay becomes enormous. The implications of this are staggering. Everything you know about the universe comes from old information. The universe you see when you look through a telescope is a universe that used to exist. The current state of distant space is unknowable. You are trapped in the past, watching recordings, unable to fast forward to the present. And this leads us to a deeply disturbing possibility. If something catastrophic happened out there, if stars started dying, if galaxies disappeared, if the fabric of space itself started tearing apart, you would not see it immediately. You would see it only when the light carrying that information finally reached Earth. And by then, whatever happened might be spreading toward you, and you would have no way of knowing until it arrived. Building the time machine in reverse. Now that you understand that looking at distant objects means looking into the past, let us take a journey outward from Earth and see just how deep into history we can travel simply by looking at progressively more distant objects. The universe becomes a time machine, and distance is the dial we turn to go further and further backward. We have already discussed the Sun at 8 light minutes away, showing us 8 minutes into the past. Let us move outward. The planet Jupiter, depending on where Earth and Jupiter are in their orbits, sits somewhere between 30 to 50 light minutes away. When you look at Jupiter through a telescope, you are seeing it as it was roughly 40 minutes ago. If a massive asteroid struck Jupiter right now, astronomers on Earth would not observe the impact for another 40 minutes. Moving further out, we reach Neptune, the most distant planet in our solar system, sitting about 4 light hours away. Looking at Neptune means looking 4 hours into the past. When the sun rose this morning, Neptune was in a position you will not be able to observe until this afternoon. Now we leave our solar system entirely and enter interstellar space. The nearest stars, as mentioned, are about 4 light years away. But most stars you can see with your naked eye are much farther. Sirius, the brightest star in our night sky, sits 8.6 light years away. You are seeing it as it was 8.5 years ago. Betelgeuse, the red supergiant star in the constellation Orion, sits about 550 light years away. When you look at Betelgeuse, you are seeing light that left that star in the 1500s, before the founding of the first permanent English settlement in North America. But stars are just the beginning. Let us look at entire galaxies. The Andromeda Galaxy, our nearest large galactic neighbour, sits approximately 2.5 million light-years away. When you look at Andromeda, even with the naked eye on a dark night, you are seeing that galaxy as it existed 2.5 million years ago. At that time on Earth, our human ancestors were primitive creatures just beginning to use stone tools. Homo sapiens did not even exist yet. The light you see from Andromeda is older than modern humans. Think about what this means. Andromeda contains roughly 1 trillion stars. Right now, at this very moment, those trillion stars are in some configuration, doing whatever stars do. Some might be exploding as supernovae. Some might be forming from clouds of gas. Some might have planets orbiting them where alien civilizations have risen and fallen. But you cannot see any of that current activity. You can only see what those trillion stars were doing 2.5 million years ago when our ancestors were barely learning to walk upright. Now let us go deeper. The Triangulum galaxy sits about 3 million light-years away. The Sombrero galaxy sits about 30 million light-years away, showing you the universe as it was when Earth's continents were in completely different positions and life was still confined to the oceans. The Virgo cluster of galaxies, containing thousands of galaxies, sits roughly 60 million light-years away. The light you see from those galaxies began its journey to Earth when dinosaurs still walked the planet, millions of years before the asteroid impact that would cause their extinction. But we can look even further back. With powerful telescopes, we can observe galaxies that are billions of light-years away. These galaxies show us the universe as it was when our Sun did not even exist yet, when our solar system was just a cloud of gas and dust that had not yet collapsed to form planets. We are looking back to a time before Earth existed, before any of the atoms in your body had been assembled into anything resembling you. The most distant objects we can observe are nearly 14 billion light-years away, showing us the universe when it was only a few 100 million years old, in its cosmic infancy. These ancient galaxies look different from modern galaxies. They are smaller, more irregular, still in the process of forming. We are watching the universe grow up, seeing its childhood captured in light that has been traveling toward us for almost the entire age of the universe itself. This is one of the most profound aspects of astronomy. We do not just study space, we study time. Every observation is archaeological. We are digging through layers of cosmic history, peeling back billions of years, watching the story of existence unfold in reverse as we look further and further away. But now comes the truly unsettling part. For every object we observe, we are seeing its past. We have absolutely no idea what any of these objects look like right now. Andromeda might have collided with another galaxy 2 million years ago, completely changing its structure, but we will not see that collision for another 500,000 years when the light from that event finally reaches us. Distant galaxies, billions of light-years away, might have been swallowed by massive black holes, might have had all their stars burn out, might have been destroyed by phenomena we do not even understand yet. But we still see them as they were billions of years ago, shining peacefully in our telescopes. The universe we observe is a ghost. It is an echo. It is a recording of what used to be. And the further we look, the older the recording becomes. We are living in a bubble of delayed information surrounded by light from the past, with absolutely no way to know what is actually happening right now beyond our immediate neighborhood. This is not a problem we can solve with better technology. We cannot build a telescope that sees the present. The speed of light is an absolute limit built into the structure of space-time itself. We are fundamentally and permanently trapped behind a wall of cosmic time delay. The terrifying implication. Now we arrive at the question that should be making you deeply uncomfortable. If everything we see in the universe is showing us the past, and we have no way to observe the present in distant regions, then how can we possibly know that the universe is still alive out there? When I say the universe might be dead, I'm not talking about some vague philosophical concept. I'm talking about the very real possibility that in regions of space we cannot currently observe in their present state, the physical conditions necessary for stars, galaxies, and matter as we know it to exist might have ended. The universe might have undergone some catastrophic transition that destroyed or fundamentally changed everything in its path. And because we can only see the past, we would still be looking at light from before that transition occurred. Imagine you are watching a movie of someone's life. The movie shows them healthy, happy, going about their day. But this movie was filmed 10 years ago. The person you're watching in the movie might have died 9 years ago. The movie does not show you their death because it had not happened yet when the movie was filmed. You are watching them alive on screen, but they are gone in reality. The recording and the present state are completely disconnected. This is our relationship with the distant universe. We are watching a movie filmed millions or billions of years ago. The stars we see are actors on screen. They were alive when the movie was filmed, but we do not know if they are still alive now. You might be thinking, surely scientists would have some way of detecting if something catastrophic was happening to the universe. Surely there would be signs, warning signals, some indication that something was wrong. And you would be partially correct. If the universe were dying in certain ways, we might see evidence of it approaching. But here is the deeply unsettling truth. Many of the ways the universe could end would give us no warning whatsoever. Consider this scenario. Somewhere in the universe, millions of light years away, reality itself fundamentally changes. The laws of physics that govern how atoms work, how chemistry functions, how stars burn, all of those rules suddenly shift to something completely different. This change spreads outward in a bubble, expanding at the speed of light. Everything the bubble touches is instantly transformed or destroyed according to new physical laws. Now, here is the terrifying part. This bubble is moving toward us at light speed. The light that shows us the region of space where the bubble originated cannot travel faster than the bubble itself. This means we cannot see the bubble coming. The last moment of light we receive from that region shows everything as normal because that light left before the transition occurred. The next moment the bubble arrives and reality as we know it ends. There is no warning. The information about the danger and the danger itself arrive at the same time. It would be like standing on train tracks, looking down the rail into the distance. You see nothing coming. The tracks look clear. But unbeknownst to you, there is a train approaching at the speed of light. Light from the train cannot reach your eyes before the train itself reaches your body, because both the train and the light from the train are traveling at the same speed. You would see empty tracks right up until the moment of impact. You would never see it coming. This is not a comforting thought. It means that right now, as you read this, as you breathe, as you exist, there could be a wave of cosmic destruction spreading through the universe, rewriting reality, and we would have absolutely no idea it was happening until the moment it reached us. The universe could be dying from the outside, with regions we cannot observe in their current state already gone. And we are sitting here watching old light from those regions, thinking everything is fine. Even if the universe is not actively being destroyed, there is still the question of its natural death. Everything that exists must eventually come to an end. Stars burn out, galaxies merge and collide. Even black holes, the most enduring objects we know of, eventually evaporate through a process called Hawking radiation over incomprehensible timescales. The universe itself has a life cycle. It was born in the Big Bang. It is currently in its mature phase, and someday, in the far future, it will reach its end. But what if that end is not as far in the future as we think? What if our calculations are wrong? What if the universe is aging faster than we realize, or some process we do not understand is accelerating its death? We wouldn't know until we started seeing distant regions go dark as their stars burned out faster than expected. And by the time that light reached us to show us the end approaching, the present state of those regions would be even further along in their death process. We are living with profound uncertainty. The night sky looks peaceful. Stars twinkle, galaxies shine. Everything appears stable and enduring. But that stability is an illusion created by time delay. We are looking at ancient light, at recordings of how things used to be. The present could be completely different, and we would not know. This leads us to ask, what are the ways the universe could actually die? What mechanisms could end reality as we know it? And if any of these processes have already begun in distant regions, what would that mean for us here on Earth? These are the questions we must now explore. The heat death. When energy runs out, let us begin by exploring the most widely accepted end for the universe, a death so slow and inevitable that it is written into the fundamental laws of thermodynamics. This is called heat death, and to understand it, we need to talk about something you encounter every single day: entropy. Imagine you have a cup of hot coffee sitting on a table in a cool room. What happens over time? The coffee gets colder. The heat from the coffee spreads out into the surrounding air. Eventually, the coffee reaches room temperature and it stays there. The heat has not disappeared. It has been distributed. The concentrated warmth that was in the coffee has spread out evenly through the room. This is entropy at work. Entropy is a measure of how spread out and disordered energy is in a system. Heat naturally flows from hot objects to cold objects, from concentrated to dispersed, from ordered to chaotic. This is the second law of thermodynamics, one of the most fundamental rules in all of physics. Entropy always increases in a closed system. Things always move toward greater disorder. You see this everywhere. If you drop a glass, it shatters into many pieces. Those pieces do not spontaneously reassemble themselves into a glass. A melting ice cube turns into water and spreads out. The water does not gather itself back into a perfect ice cube. Perfume sprayed in a corner of a room gradually disperses throughout the entire room. It does not all spontaneously collect back into the corner. These are all examples of entropy increasing, of order becoming disorder, of concentrated energy becoming spread out. Now scale this up to the entire universe. The universe is full of pockets of concentrated energy. Stars are burning hydrogen, fusing it into heavier elements, releasing enormous amounts of energy in the process. This energy radiates out into space as light and heat. Black holes contain tremendous gravitational energy. Planets have kinetic energy as they orbit. Atoms themselves contain energy in the bonds between their parts. But all of this energy is slowly spreading out. Stars are burning their fuel, converting concentrated nuclear energy into scattered photons of light that disperse through space. Those photons travel outward, their energy getting thinner and thinner as it spreads across larger and larger volumes of space. Eventually, every star will run out of fuel. The Sun will burn through all its hydrogen in about 5 billion years, swell into a red giant, shed its outer layers, and collapse into a white dwarf that slowly cools over trillions of years until it becomes a cold, dark cinder. This will happen to every star. Small stars will burn slowly, but eventually die. Large stars will burn quickly, explode as supernovae, and leave behind neutron stars or black holes. But even those remnants will eventually decay. Black holes, despite their name, are not entirely black. They emit something called Hawking radiation, a quantum process that causes them to very slowly evaporate. A black hole with the mass of our Sun would take 10 to the power of 67 years to completely evaporate. That is a 1 followed by 67 zeros, a time span so vast that the current age of the universe, 14 billion years, is less than a blink of an eye in comparison. But even that unimaginable length of time is not forever. Wait long enough, and every black hole will evaporate. Every star will burn out. Every atom might eventually decay through processes we do not fully understand, but that physics suggests are possible over truly cosmic timescales. What you're left with is heat death. The universe becomes a cold, dark, uniform sea of incredibly thin, scattered energy. The temperature everywhere is the same, just a tiny fraction above absolute zero, the coldest possible temperature. There are no stars shining, no galaxies swirling, no planets orbiting, just diffuse, scattered particles and radiation spread so thin that nothing interesting can ever happen again. Why can nothing happen? Because interesting events require energy differences. A ball rolls down a hill because there is a difference in gravitational potential energy between the top and bottom. Your body functions because there is a difference in chemical energy between the food you eat and the waste you excrete. Stars shine because there is a difference between the nuclear energy in their cores and the cold emptiness of space around them. Everything that happens, every process, every change, requires some form of energy gradient, some difference that can be exploited to do work or cause change. In a universe at heat death, there are no differences. Everything is uniform. The same temperature, the same density, the same state. There is no high and low, no hot and cold, no concentrated and dispersed. Without differences, nothing can flow, nothing can change, nothing can happen. The universe reaches a state of maximum entropy, maximum disorder, where it will remain forever. This is the ultimate fate predicted by our understanding of thermodynamics. It is not a death by explosion or collapse. It is death by equilibrium. The universe does not end with a bang, but with a whimper, slowly fading away as all its energy spreads out into cold, dark, eternal stillness. Now, scientists calculate that this heat death is incredibly far in the future. We are talking about time scales that make the current age of the universe look like a brief moment. 10 to the power of 100 years or more. Numbers so large that they become almost meaningless to human comprehension. But here is where the unsettling part comes in. What if time does not work the way we think it does across cosmic distances? What if the heat-death process can happen at different rates in different regions of the universe? What if somewhere far beyond what we can observe, a region of the universe has already reached heat-death? Its stars have all burned out. Its black holes have all evaporated. It has become a cold, dead, empty void. And now the boundary between that dead region and the still living regions is spreading outward. Not as a physical wave, but as a condition. As the dead region grows, more and more of the universe falls into equilibrium, and the process accelerates. The living portions of the universe are like islands in an expanding ocean of nothingness. We would not see this happening. Light from those distant regions shows us stars still burning, galaxies still shining, because that light is OLD. It left before the heat-death process completed in those regions. By the time we see stars in a distant galaxy begin to fail, by the time the light shows us that region going dark, the actual current state of that region might be far more advanced in its death. The death could be spreading toward us, and we would not know until it was far too late. The universe could be dying from the outside in, slowly succumbing to the inevitable increase of entropy, with only a shrinking bubble of active, energetic space remaining. And we, sitting in our small corner, watching old light from all directions, would think everything was fine until the darkness finally reached us. This is the terror of heat death combined with the time delay problem. The end might not be trillions of years away. The end might have already begun in regions we cannot observe in their present state. And we would not know until the information about that death finally traveled across space to reach us, by which time it might be far too late to do anything about it. False vacuum decay, reality's hidden trapdoor. Heat, death is slow, inevitable and depressing in its gradual grinding down of all energy and order. But there is another way the universe could end that is far more sudden, far more violent, and far more absolutely unstoppable. This is called false vacuum decay, and it is one of the most terrifying possibilities in all of physics. To understand this, I need to first explain what physicists mean by a vacuum. In everyday language, a vacuum is just empty space, nothing there. But in quantum physics, even empty space is not truly empty. The fabric of space itself has energy. This is called the vacuum energy, and it represents the lowest possible energy state that space can have. Think of it as the baseline level of energy that exists everywhere, even in the absence of any matter or radiation. Now imagine a landscape with hills and valleys. A ball sitting in a valley is in a low energy state. It is stable there. If you push it slightly, it will roll back to the bottom of the valley. But imagine there is a deeper valley hidden below, separated by a barrier. The ball is sitting in a shallow valley, which seems like the lowest point from its perspective. But there's actually an even lower valley that the ball does not have access to yet. This shallow valley is what physicists call a false vacuum. It seems like the lowest energy state, but it is not the true lowest energy state. The deeper valley is the true vacuum. The ball is temporarily stable in the false vacuum, but if something gives it enough energy to overcome the barrier, it will roll down into the true vacuum and release a tremendous amount of energy in the process. Now, apply this to the entire universe. What if the vacuum energy of space, the baseline energy level that exists everywhere, is not in the true lowest energy state? What if our entire universe is sitting in a false vacuum, temporarily stable but not truly at the bottom? What if there is a lower energy state that space could transition to, releasing enormous energy in the process? This is not just wild speculation. It emerges from serious theories in particle physics. The Higgs field, which gives particles their mass, might exist in a false vacuum state. The universe might be metastable, meaning it seems stable now, but could potentially transition to a different state. If this transition happens, it would occur through a quantum process. At some random point in space, purely by chance, a tiny bubble of true vacuum would form. Inside this bubble, the laws of physics would be different. The particles that make up atoms would have different masses. The forces between particles would have different strengths. Chemistry as we know it would not work. Stars could not burn. Atoms might not even be stable. And here is the terrifying part: this bubble would expand at the speed of light. The true vacuum state is lower energy than the false vacuum, which means the bubble grows explosively, with the energy difference between the two states being released at the boundary. Anything the bubble touches is instantly transformed. Atoms are ripped apart and reassembled according to the new physical laws. Any structure, any complexity, any order is destroyed. The wall of the bubble races outward at light speed, rewriting the rules of physics as it goes. And because it moves at the speed of light, we cannot see it coming. Light carrying information about the bubble cannot travel faster than the bubble itself. The last light we receive from a region of space before the bubble hits shows everything as normal, because that light left before the transition occurred. Then the bubble arrives and reality ends. You would not feel pain. You would not have time to be afraid. One moment you exist, the next moment the wave of changed physics passes through you and you are gone, transformed into something unrecognizable, scattered into whatever forms matter takes in the new vacuum state. The Earth would be destroyed. The Sun would be destroyed. The entire solar system would be rewritten in an instant, and the bubble would keep expanding. It would consume our galaxy. It would consume neighboring galaxies. It would spread through the universe, turning everything it touched into a region governed by new and possibly incompatible laws of physics. Any life, any structure, any information would be erased at the boundary. Now, here is the deeply unsettling question. What if this has already happened? What if somewhere in the universe, millions or billions of light years away, a false vacuum decay bubble formed and began expanding? It could have happened yesterday or a billion years ago. It could be racing toward us right now, and we would have absolutely no way of knowing. The light we see from that region still shows the old vacuum state, because that light is old. It left before the transition. We look in that direction and see galaxies shining peacefully, completely unaware that those galaxies might have been destroyed long ago and replaced with something unrecognizable. The bubble could be halfway across the observable universe, consuming everything in its path, and we would not see any evidence of it until the moment it arrived here and ended everything. There is no defense against this. You cannot outrun something moving at the speed of light. You cannot shield yourself from a change in the fundamental laws of physics. If a false vacuum decay bubble is heading our way, the universe as we know it is already doomed. We just do not know it yet. The only comfort, if you can call it comfort, is that physicists generally think our vacuum is probably stable, not false. Measurements of the Higgs field suggest we might be in a true vacuum, after all, or at least in a false vacuum that is stable enough that the probability of decay is incredibly low. The universe has existed for nearly 14 billion years without this happening, which suggests that if we're in a false vacuum, the barrier between it and the true vacuum is very high, making transitions extremely unlikely. But unlikely is not the same as impossible. Quantum mechanics is fundamentally probabilistic. Even incredibly unlikely events can happen, just rarely. The universe is vast. Time is long. Somewhere, somewhen, the improbable might occur. And if it already occurred somewhere beyond our ability to observe the present state, we will not know until the bubble arrives. The universe could be being destroyed right now, and we would sit here watching old light from destroyed regions, thinking everything was fine, right up until the moment reality itself is rewritten around us. This is perhaps the most horrifying cosmic death scenario because of its suddenness and its inevitability once started. Heat death at least gives warning signs as stars burn out. But false vacuum decay gives no warning. It is the universe's hidden trapdoor, and we will not know if we are falling through it until we have already fallen. The Big Rip. When expansion wins, we have explored heat death, the slow grinding down of all energy differences until nothing can happen anymore. We have explored false vacuum decay, the sudden rewriting of physical laws that destroys everything instantly. Now let us explore a third possibility, one that combines elements of both the slow and the sudden, the gradual and the catastrophic. This is called the Big Rip, and it is what happens if the expansion of the universe never stops accelerating. To understand the Big Rip, you first need to know that the universe is expanding. This is one of the most important discoveries of 20th century science. In the 1920s, astronomer Edwin Hubble observed that distant galaxies are moving away from us. The further away a galaxy is, the faster it is receding. This is not because galaxies are moving through space away from us. Rather, space itself is stretching, carrying galaxies apart like dots drawn on the surface of an inflating balloon. For decades, scientists assumed this expansion would gradually slow down. After all, gravity pulls everything together. The mutual gravitational attraction between all the matter in the universe should act as a brake, slowing the expansion over time. Perhaps the universe would expand forever, but at an ever-decreasing rate, asymptotically approaching a standstill. Or perhaps gravity would eventually win, and the universe would stop expanding and begin contracting, eventually collapsing back into a big crunch, the opposite of the Big Bang. But in the late 1990s, astronomers made a shocking discovery. They measured the expansion rate of the universe at different points in its history by looking at distant supernovae, exploding stars that act as cosmic distance markers. And they found that the expansion is not slowing down. It is speeding up. The universe is expanding faster and faster as time goes on. This discovery won the Nobel Prize in Physics because it was so unexpected and important. Something is pushing space apart, counteracting gravity, causing the expansion to accelerate. Scientists call this mysterious force dark energy, but that is really just a name for our ignorance. We do not know what dark energy is. We do not know where it comes from. We just know it exists because we can measure its effects. Dark energy makes up about 68% of the total energy content of the universe. It dominates everything else. And if its strength remains constant or increases over time, the universe will continue expanding faster and faster forever. For most of cosmic history, this accelerating expansion is relatively benign. Galaxies move away from each other, but galaxies that are bound together by gravity, like our Milky Way and the nearby Andromeda galaxy, will eventually merge rather than being pulled apart. Gravity on small scales is strong enough to overcome the expansion of space. Galaxy clusters stay bound together. Solar systems stay intact. The Earth keeps orbiting the Sun. But here is where the Big Rip scenario comes in. What if dark energy does not remain constant? What if it grows stronger over time? If the accelerating expansion keeps accelerating, eventually it could overcome gravity even on small scales. First, distant galaxy clusters would be pulled apart as the expansion becomes too strong for their gravity to hold them together. We would see these clusters disperse, galaxies flying away from each other faster than light can bridge the gap. They would disappear beyond our cosmic horizon, the boundary beyond which light can no longer reach us because space is expanding too fast. Our observable universe would shrink. Not physically shrink, but the portion we can observe would get smaller and smaller as more and more distant objects are carried away faster than light can travel to us. Eventually, our local group of galaxies would be all that remains visible. Everything else would have disappeared beyond the horizon. But the expansion continues to accelerate. Now it starts overcoming the gravity holding individual galaxies together. Stars would be pulled away from galactic centers. Our Milky Way would dissolve, with stars streaming away in all directions as space stretches faster than gravity can pull them back. Then the expansion becomes strong enough to overcome the gravity-holding solar systems together. The planets would be ripped away from the Sun. The Moon would be torn from Earth's orbit. Our planet would find itself alone in space, no longer part of any larger structure. But it does not stop there. The expansion keeps growing stronger. Now it begins to overcome the forces holding planets together. The Earth's own gravity cannot resist the expansion of space. The planet would be torn apart, ripped into fragments that themselves are pulled away from each other. And still, the expansion accelerates. Now it overwhelms the electromagnetic forces holding molecules together. Your body, made of countless molecules, would be ripped apart at the molecular level. Then atoms themselves would be shredded as the expansion overcomes the forces binding electrons to nuclei. Finally, even atomic nuclei would be torn apart, protons and neutrons separated, and ultimately even those particles would be ripped to pieces as space expands faster than the fundamental forces can hold matter together. This is the Big Rip. The universe does not end in darkness and cold like heat death. It does not end in a sudden rewriting of physics like false vacuum decay. It ends in being torn apart at every scale, from the largest cosmic structures down to the smallest subatomic particles. Everything is pulled apart by an expansion so powerful that no force in nature can resist it. When would this happen? That depends entirely on the behavior of dark energy, which we do not fully understand. If dark energy remains constant, the Big Rip never occurs. The universe expands forever, but gravity and other forces continue to work normally on local scales. But if dark energy grows stronger in a particular way, described by something called the equation of state parameter, then the Big Rip becomes inevitable. Different calculations suggest different time scales. Some models put the Big Rip tens of billions of years in the future. Others suggest it could be as soon as 20 billion years from now. That sounds like a long time, but cosmically speaking, it is not. The universe is currently 13.8 billion years old. 20 billion years is less than twice the current age of the universe. And here is where we return to our central theme. We do not know the current state of dark energy throughout the universe. We can only measure its effects locally and in the past by observing distant supernovae. If dark energy behaves differently in regions far from us, if it is stronger out there beyond our observational horizon, then those regions might already be experiencing the early stages of the Big Rip. Imagine a region of the universe billions of light-years away, where dark energy has become so strong that galaxy clusters are being pulled apart. The light we see from that region shows galaxies peacefully gravitationally bound, because that light is old. But in the present state of that region, which we cannot observe, those clusters might have already dispersed. And if the process is spreading, if the strengthening of dark energy is moving through space like a wave, it could be heading toward us. We would not see it coming until we observe distant galaxies beginning to disperse, and by the time that light reached us, the actual front of the phenomenon would be much closer. We might see galaxy clusters falling apart 1 billion light-years away, but that happened 1 billion years ago. The boundary of the Big Rip might now be only 1 million light-years away, racing toward us, and we would not know for another 1 million years when the light from that closer boundary finally reached us. The Big Rip is terrifying because it is thorough. Heat death leaves a cold, dark universe, but at least space itself remains intact. False vacuum decay changes the laws of physics, but might create new stable structures under the new rules. The Big Rip destroys everything at every scale, leaving behind nothing but a void where even the concept of structure has ceased to exist. Whether this will actually happen depends on the nature of dark energy, which remains one of the biggest mysteries in physics. But the fact that we cannot know the current state of dark energy in distant regions means we cannot rule out the possibility that somewhere far beyond our sight, the universe is already beginning to tear itself apart. We have explored 3 catastrophic ways the universe could die: heat death through entropy, false vacuum decay through quantum tunneling, the Big Rip through runaway expansion. Each of these scenarios is frightening in its own way, but underlying all of them is a deeper problem, one that goes beyond any specific mechanism of cosmic death. This is the perception problem, and it fundamentally shapes what we can and cannot know about reality. Let us return to the basic fact we established at the beginning. Light travels at a finite speed, and therefore looking at distant objects means looking into the past. This seems straightforward enough when we are talking about stars and galaxies, but the implications run much deeper than you might realize. Everything you perceive, even in your immediate surroundings, is technically in the past. Light bouncing off your hand takes a tiny fraction of a second to reach your eyes. Sound from someone speaking takes longer to reach your ears than light from their moving lips. Your brain receives all these signals at slightly different times and stitches them together into what feels like a unified present moment. But that present moment is actually a reconstruction, a model your brain builds from delayed information. The delay is so small in everyday life that it does not matter. 1/1,000,000th of a second or 1,000th of a second makes no practical difference. But the principle is the same whether we are talking about light from your hand or light from a distant galaxy. All perception is delayed. All observation is of the past. There is no way around this fundamental limitation. Now, let us think about what this means for the concept of now. When you say something is happening right now, what do you mean? You mean it is happening at the present moment as you experience it. But your experience of the present is constructed from information that takes time to reach you. For you, the present is defined by what you can observe and interact with. But here is where things get strange. According to Einstein's theory of relativity, there is no universal now. Two observers moving at different speeds relative to each other will disagree about whether two distant events happened at the same time. They will both be correct from their own frame of reference, but their frames do not match. The concept of simultaneity, of things happening at the same moment, is not an absolute fact of the universe. It is relative to your motion and position. This means that when you ask whether a distant galaxy exists right now in this moment, you are asking a question that does not have a single objective answer. Right now, according to whom? According to an observer at rest relative to the galaxy? According to an observer at rest relative to Earth? According to an observer moving at high speed between them? Each observer would have a different slice through space-time that they consider the present moment, and these slices would not agree about distant events. This is deeply unsettling. It means the universe does not have a single present moment that all observers share. The present is local, not global. You can define a present moment for yourself and your immediate surroundings, but you cannot extend that definition to the entire universe in an objective way. What does this mean for our question about whether the universe is dead? It means the question itself is not well posed. Asking if the universe is dead right now requires specifying what we mean by right now, and that specification depends on our reference frame. From our perspective here on Earth, the present state of a galaxy 10 billion light-years away is simply not accessible. It is not part of our present. It lies outside what is called our light cone, the region of space-time that we can have causal contact with. Your light cone extends backward in time to include everything that could have influenced you, and forward in time to include everything you could potentially influence. The present state of distant regions lies outside your light cone. It is not in your past, because light from that present state has not reached you yet. It is not in your future, because you cannot affect it. It is in a region of space-time that is simply disconnected from your present moment. This is not a limitation of technology or observation. This is a fundamental feature of how space-time works. The structure of the universe is such that there are regions whose present state is fundamentally unknowable to you, not because the information is hidden, but because that region's present is not part of your present. You and that distant region exist in causally disconnected slices of time. What you can know is the past state of that region, the state it was in when light left it that is now reaching you. You can build models to predict what its present state might be, based on physical laws and the trajectory of its past evolution. But you cannot observe its present directly. And if your models are wrong, if something unexpected happened, you will not find out until light from that unexpected event reaches you. This is the perception problem. We are not just limited in what we can see. We are fundamentally limited in what we can know about the present state of distant space. The universe could be in a vastly different condition out there beyond our light cone, and we would have no way of detecting it until information from those regions finally reaches us. Now, think about what this means for the cosmic death scenarios we discussed. If heat death has progressed further in distant regions, we will not see it until light from those darker regions arrives. If a false vacuum decay bubble is expanding toward us, we will not detect it until it reaches us. If the Big Rip is already pulling apart galaxies beyond our horizon, we cannot observe it yet. We are living in a bubble of knowable past information, surrounded by an unknowable present that extends in all directions. And the further away from us we look, the older the information becomes, and the larger the gap between what we see and what currently exists. This is the fundamental constraint on cosmology. We can see the universe's past with great clarity. We can observe how galaxies formed, how stars evolved, how structure emerged from the primordial fireball of the Big Bang. But the universe's present, its current state across its full extent, is hidden from us. We can only infer it, model it, predict it. We cannot observe it. And if something unexpected is happening out there, something our models do not account for, we will not know until the information finally arrives. By which time, whatever is happening might be much closer, much further along, much more advanced than the information shows us. We are flying blind into the future, navigating based on a map that only shows us where things were, not where they are. The observable universe boundary. To truly understand the depth of our ignorance about the universe's present state, we need to confront one of the most profound concepts in cosmology, the observable universe. This is the region of space from which light has had enough time to reach us since the Big Bang. Beyond this region lies more universe, possibly infinitely more, that we cannot see, because light from there has not had time to arrive yet. Let me explain how this works. The universe began approximately 13.8 billion years ago in the Big Bang. Light travels at a finite speed. Therefore, the furthest we can possibly see is the distance light could have traveled in 13.8 billion years. You might think this means the observable universe has a radius of 13.8 billion light-years, but actually it is larger than that, because the universe has been expanding during the time light has been traveling. When we account for this expansion, the radius of the observable universe is approximately 46 billion light-years. This creates a sphere around us, with Earth at the center, not because we are actually at the center of the universe, but because we can only observe the region around us from which light has had time to reach us. An observer in a distant galaxy would see their own observable universe sphere centered on them, and their sphere would overlap with ours, but would also extend into regions we cannot see. Here is the crucial point. The observable universe is not the entire universe. It is just the part we can see. The full universe extends beyond our observable sphere. We do not know how far it extends. It might be just slightly larger than what we can observe. It might be vastly larger. It might be infinite. And we have no way of knowing what lies beyond our observable boundary. We cannot see it. We cannot measure it. We cannot interact with it. It is fundamentally and permanently beyond our reach, not because we lack powerful enough telescopes, but because light from those regions has not had enough time to cross the expanding space between there and here. Now, here is where things become even more strange. Because the universe is expanding, some regions that were once within our observable universe are now moving away from us so fast that they are crossing out of our observable universe. The expansion of space can make distant objects recede from us faster than light, which sounds like it violates the rule that nothing can move faster than light, but it does not. Objects cannot move through space faster than light, but space itself can expand at any rate, carrying objects apart faster than light could travel between them. This means there is a horizon beyond which objects are receding from us faster than light. Light from those objects cannot reach us anymore because the space between us and them is expanding faster than light can cross it. These objects are disappearing beyond our cosmic horizon, and we will never see them again. The information about their present state will never reach us. Ever. This is permanent, absolute, total information loss. There are regions of the universe whose present and future states are forever unknowable to us, not because of any technological limitation, but because of the fundamental structure of space-time and cosmic expansion. Now, think about what this means for our central question. Out there, beyond our observable universe boundary, there could be trillions of galaxies, vast cosmic structures, regions of space undergoing processes we cannot imagine. And some of those regions might be dying. Stars might have burned out. False vacuum decay might have occurred. The Big Rip might be tearing things apart. Or something entirely different might be happening, something we have not even conceived of because we have never seen evidence of it in our observable region. And we would have absolutely no way of knowing. Those regions are completely cut off from us. Light from them will never reach us. No information can ever arrive to tell us what is happening there. They might as well be separate universes entirely, causally disconnected from ours. But here is the truly unsettling part. The boundary between the observable and unobservable universe is not fixed in space. It is constantly changing as time passes and light from more distant regions reaches us. New galaxies that were previously too far away for their light to have reached us are gradually becoming visible as their light finally completes its journey. However, because of cosmic expansion, we are also losing galaxies on the far edge of our observable universe as they cross the horizon and recede faster than light. The observable universe is not just a sphere around us. It is a dynamic sphere, with new regions entering at the boundary while others exit at the far edge. This means that what is currently beyond our observable universe might not always be beyond it. Light from some of those regions is traveling toward us right now and will eventually arrive. When it does, we will finally see what those regions look like when the light left them. but we still will not know what they look like now. We will just be seeing further into the past of regions that were previously too distant to observe. So imagine this scenario. 1 trillion light-years away, far beyond our current observable universe boundary, a catastrophic event occurs. Perhaps a false vacuum decay bubble begins expanding. Perhaps dark energy suddenly strengthens and begins tearing galaxies apart. Perhaps something we cannot even imagine happens that fundamentally changes the nature of space in that region. This event occurred, let us say, 11 billion years ago. At that time, Earth did not even exist yet. Our solar system had not formed, but light from that event began traveling toward the region of space where Earth would eventually be. For 11 billion years, that light has been traveling through expanding space, slowly crossing the vast distance. The event itself happened long ago. The region where it occurred might have undergone complete transformation. The catastrophe might have spread, growing larger, consuming more and more of space. But we do not see any of this yet, because the light has not reached us. Now, 2 billion years from now, that light finally enters our observable universe. Astronomers of whatever civilization exists on Earth at that time see this light and realize that something catastrophic happened in a distant region 11 billion years ago. But they have no idea what the current state of that region is. They are seeing the beginning of an event that is now 13 billion years old. Who knows how far it has progressed? Who knows how close it has come to us? This is the horror of the observable universe boundary. We are constantly receiving information from regions that were previously too distant to observe, and that information is incredibly OL'd by the time it arrives. We are seeing the distant past gradually come into view, but we have no idea what the present state of those newly visible regions is. The universe beyond our observable boundary could be in the process of ending right now, and we would not know until light from that ending finally reached us billions of years from now, by which time the actual present state of those regions would be billions of years further advanced in their death process. We are surrounded by mystery. In every direction, beyond what we can currently see, lies an unknowable expanse whose present condition is hidden from us. And the further away we look within our observable universe, the older the information becomes, until at the very edge we are seeing light from galaxies as they were in the early universe, more than 13 billion years ago. Those galaxies might not even exist anymore in any form we would recognize. They could have collided with other galaxies, been torn apart by gravitational interactions, fallen into massive black holes, or undergone any number of transformations. But we still see them as they were 13 billion years ago, frozen in time by the delay of light. The universe we observe is not the universe that exists. It is a museum of cosmic history, showing us different eras depending on which direction we look and how far away we are observing. And the present, the actual now, across all of space, is completely hidden from us, unknowable, inaccessible, separated from us by the fundamental structure of causality and space-time. This is perhaps the most profound limitation on human knowledge. We can never know the full present state of the universe. We can only know the past and we can only speculate about the present based on models and assumptions. If those models are wrong, we will not find out until it is too late. The information problem. We have established that we cannot directly observe the present state of distant regions of the universe. But you might be thinking, surely we can calculate what is happening out there. After all, physics gives us laws that govern how matter and energy behave. If we know the past state of a region, and we know the laws of physics, can we not simply calculate what the present state must be? This is a reasonable thought, and it is exactly what cosmologists do when they build models of the universe. They take observations of the past, apply known physical laws, and extrapolate forward to predict what things should be like now. But this process is not as straightforward or reliable as you might hope. There are several deep problems with using calculation to substitute for observation. The first problem is that the universe is not deterministic at the quantum level. Quantum mechanics, the physics that governs the smallest scales of reality, is fundamentally probabilistic. When you measure a quantum system, you do not get a determined result. You get one of several possible results with probabilities for each outcome. The universe makes random choices at the quantum level, and these random choices accumulate to affect larger scales over time. This means that even if you knew the exact state of a region of the universe at some point in the past, you could not calculate with certainty what that region looks like now. You could calculate probabilities for different outcomes, but you could not say definitively which outcome actually occurred. The universe's evolution has an element of genuine randomness built into it at the most fundamental level. For most purposes, this quantum randomness averages out over large scales. Individual atoms might behave unpredictably, but a planet containing trillions of atoms behaves in a statistically predictable way. But when we are talking about rare events like false vacuum decay, quantum randomness becomes crucial. Such events are quantum processes. They happen with very low probability in any given region at any given time. But over vast scales of space and time, improbable things can happen. We cannot predict where or when. We can only say that somewhere, sometime, they might occur. The second problem is that our observations of the distant universe are incomplete. We can only see the light that reaches us, but light is not the only messenger. The universe also produces gravitational waves, neutrinos, cosmic rays, and possibly other forms of information we have not yet discovered. We detect only a fraction of these other messengers because they are hard to observe and our detectors are limited. This means our picture of the distant universe is incomplete. We are like someone trying to reconstruct a conversation by reading only every 10th word. We can get the general idea, but we miss important details. There could be phenomena happening in distant regions that do not produce much light, but do produce other signals we are not detecting. Our models might be missing entire classes of events or processes. The third problem is that our laws of physics might be incomplete or wrong. This sounds shocking, but it is important to maintain humility. Physics is not a collection of eternal, absolute truths handed down from on high. It is a collection of models that we have built to explain our observations. These models work extremely well within the domains we have tested them, but we have no guarantee that they work perfectly everywhere in the universe or under all conditions. We already know our current physics is incomplete. General relativity describes gravity beautifully, but breaks down at the quantum scale. Quantum mechanics describes small scales beautifully, but is not integrated with gravity. We do not have a complete theory of quantum gravity. We do not fully understand dark matter or dark energy, which together make up 95% of the universe's energy content. Our models describe their effects, but not their nature. There could be physics we do not yet know about that becomes important under conditions we have not observed. High energies, extreme densities, vast scales, or long time scales might reveal new phenomena. The early universe might have operated under slightly different rules. Distant regions might have properties we have not accounted for. We build our physics models based on what we can observe and test locally, but the universe is not obligated to be the same everywhere. The fourth problem is sensitivity to initial conditions. Some systems are chaotic, meaning that tiny differences in starting conditions lead to vastly different outcomes over time. Weather is a classic example. You cannot predict the weather a month from now with precision because the atmosphere is chaotic. A tiny error in your measurement of today's conditions or a small random fluctuation gets amplified over time until your prediction diverges completely from reality. The universe is not chaotic in quite the same way that weather is, but it does have elements of sensitivity to conditions. The formation of galaxies, the distribution of matter, the behavior of dark energy. All of these are influenced by countless small factors that we cannot measure perfectly. Over billions of years, small uncertainties compound. Our predictions become less reliable the further into the future we try to calculate, and the further across space we try to extrapolate. The fifth problem is that calculation requires assumptions. We have to assume that the laws of physics are the same everywhere. We have to assume that the universe is roughly uniform on large scales. We have to assume that dark energy behaves consistently. We have to assume that our observations of the past give us a representative sample of what the universe is like. These are all reasonable assumptions supported by evidence, but they are still assumptions, not certainties. If any of these assumptions is violated in regions we cannot observe, our calculations would be wrong. The distant universe might not be uniform. Dark energy might behave differently in different regions. Physical laws might vary in ways we cannot detect locally. We have no way of checking these assumptions for the present state of regions beyond our observation. Put all of these problems together, and you see why we cannot simply calculate our way around the observation problem. Yes, we can build models that predict what distant regions probably look like now, based on what we saw in the past. And those models are our best guess, often very good guesses supported by decades of careful scientific work. But they are not certain. They are not observations. They are extrapolations that could be wrong. If something unexpected is happening out there, something our models do not predict, We will not know until we can observe it. And for regions whose present state is beyond our light cone, we cannot observe it yet. We are dependent on our models, and our models are only as good as our observations, our physics, and our assumptions. This is the information problem. We lack complete information about the past, we lack a complete understanding of physics, we face fundamental randomness at the quantum level, and we are limited by the speed of light in how fast information can reach us. All of these factors combine to create genuine uncertainty about the present state of the distant universe. The uncertainty is not just practical, something better telescopes could solve. It is fundamental, built into the structure of reality. We can reduce the uncertainty somewhat with better observations and better models, but we can never eliminate it completely. There will always be a gap between what we can observe and what we can know. And in that gap lies the possibility that the universe is very different from what we think, that something is happening beyond our sight, that the cosmos is undergoing changes we have not predicted, that death or transformation or something entirely unexpected is spreading through space, and we will not know until the information finally reaches us. Science thrives on evidence. Where evidence is lacking, we must acknowledge uncertainty. And when it comes to the present state of the universe beyond our light cone, evidence is fundamentally lacking. We have models, we have theories, we have educated guesses, but we do not have knowledge. Not yet. Not until the light carrying that knowledge completes its journey across the cosmos to reach us. Would we even notice? We have spent considerable time exploring how the universe could die and how the time delay of light prevents us from knowing the present state of distant regions. But now we must ask a practical question. If the universe were dying somewhere out there beyond our sight, would there be any warning signs? Would we detect anything unusual? Or would the end arrive completely unannounced? The answer depends on which death scenario we are talking about and where it is happening. Let us go through the possibilities. First, consider heat death. This is the gradual increase of entropy, the slow running down of energy differences until nothing can happen anymore. If heat death were progressing faster in some distant region, what would we see? We would see stars in that region burning out. We would see galaxies going dark as their stellar populations aged and died without being replaced by new star formation. This would actually give us substantial warning. Light from those dying galaxies would reach us, and we would observe them fading. We would see the signals of a region running out of energy. Astronomers would notice that galaxies in a particular direction or at a particular distance range were dimmer than expected, showing fewer young stars, exhibiting signs of advanced age. This has not been observed. When we look at distant galaxies across the universe, we see them following predictable patterns of star formation and evolution. There are no mysterious dark zones, no regions where galaxies have inexplicably burned out. The universe appears remarkably uniform in its properties across vast distances. Of course, we can only observe the past of those galaxies. They might be dying now, and we would not see it yet. But if heat death were progressing significantly faster than our models predict, we would expect to see some evidence in the observational record. We would see galaxies at different distances showing different rates of aging, with the most distant ones, whose light is oldest, showing less advanced heat death than closer ones, whose light is more recent. The progression would be visible as a gradient across space and time. We do not see this. The universe's rate of entropy increase appears consistent across all the regions we can observe. This gives us reasonable confidence that heat death is not substantially more advanced in distant regions than our models predict. But what about false vacuum decay? This is a completely different scenario. A false vacuum bubble expands at the speed of light. We established earlier that this means we cannot see it coming, because information about the bubble cannot travel faster than the bubble itself. So, would we have any warning at all? The answer is no. We would have absolutely no warning. The bubble would arrive at light speed, and the last light we receive from the region it originated in would show that region as normal, because that light left before the decay occurred. One moment we would be observing a normal, peaceful region of space. The next moment the bubble would hit us, and reality would end. There is no possible advanced detection method for a light speed phenomenon. You cannot see something approaching at light speed until it reaches you. It is like trying to outrun your shadow. The information about the danger and the danger itself arrive simultaneously. However, there is one tiny caveat. If the false vacuum bubble originated far enough away, and if it had been expanding for long enough, we might see indirect effects. The bubble would have consumed intermediate regions between its origin point and us. Those regions would now be governed by different physics. If those regions were producing any light or other signals under the old physics before the bubble arrived, those signals would stop once the bubble consumed them. So we might observe distant galaxies suddenly disappearing from view, not dimming gradually like in heat death, but vanishing abruptly. One moment visible, the next moment gone. This would be the signal that something had consumed them. And since the signal of their disappearance travels at light speed, and the bubble itself travels at light speed, we would see a wave of darkness approaching us at the speed of light, with galaxies winking out in sequence from far to near. This would give us warning, but not much. We would see the wave coming, but we could not outrun it or defend against it. We would watch distant galaxies disappear, then closer galaxies, then nearby galaxies, then finally our own galaxy and Earth. The warning would be measured in perhaps thousands or millions of years as the wave crossed the distance of our galactic neighborhood. Long enough to know what was coming, but not long enough to do anything about it, since we cannot travel faster than light and cannot change the laws of physics. Has this been observed? Are galaxies disappearing in suspicious patterns? No. The universe shows no evidence of regions being consumed by expanding bubbles of different physics. All the galaxies we observe remain visible and behave according to the physics we understand. This does not prove a bubble is not coming, but it suggests that if one is, it has not consumed any regions close enough for us to have observed yet. What about the big RIP? This is driven by dark energy strengthening and causing accelerating expansion. If the Big Rip were beginning in distant regions, what would we see? We would see galaxies in those regions being pulled apart. We would observe them becoming distorted, elongated, torn as the expansion overcame their internal gravity. This would be detectable. Astronomers study the structure and dynamics of distant galaxies carefully. If galaxies in a particular region were being ripped apart by unusually strong expansion, their shapes and motion patterns would look wrong. They would not match our models of how galaxies should behave under normal expansion rates. Again, this has not been observed. Distant galaxies look structurally normal. They rotate, interact, merge, and evolve in ways consistent with our understanding of gravity and cosmic expansion. There are no mysterious regions where galaxies are being torn apart. Additionally, we can measure the rate of expansion at different distances by observing how fast galaxies at various ranges are receding from us. If dark energy were strengthening dramatically in distant regions, we would see anomalous expansion rates. The expansion would not be uniform. Careful measurements have been made, and the expansion rate appears consistent across the observable universe, with a smoothly accelerating pattern that matches our models. There are no dramatic anomalies suggesting the Big Rip is beginning somewhere. So across all three major death scenarios, we have no observational evidence that any of them are significantly progressing in the regions we can observe in the past. The universe appears healthy, consistent, and following predictable patterns everywhere we look. Does this mean the universe is definitely not dying beyond our sight? No. It means that if it is dying, the death has not progressed far enough to have affected regions whose past light we are currently receiving. The universe's present state in distant regions could be very different from what we see, but if that difference happened recently on cosmic timescales, we would not see evidence of it yet. There is also the possibility of unknown mechanisms of death. We have discussed heat death, false vacuum decay, and the Big Rip, because these emerge from established physics. But there could be processes we have not discovered yet. Something entirely unexpected could be happening out there. Something that does not fit into our models because we have never observed anything like it before. If an unknown phenomenon were destroying distant regions, we would not necessarily recognize the warning signs. We might see strange observations, anomalies that do not fit our models, but we might attribute them to measurement error or incomplete understanding rather than recognizing them as signals of cosmic death. Science is conservative by necessity. When we see something unexpected, we first try to explain it within our existing framework. We adjust models, refine measurements, look for alternative explanations. Only after exhausting all conventional possibilities do we conclude that something truly new is happening. This means that early warnings of an unknown cosmic death mechanism might be dismissed or misinterpreted until the evidence became overwhelming. By the time we recognized the pattern, by the time we understood what we were seeing, the phenomenon might be much closer than the observations suggested, because observations show the past, and the phenomenon is progressing in the present. So, would we notice if the universe were dying? For known mechanisms, probably yes, if they are happening in regions we can observe, and if they have progressed far enough to show clear signatures. But for unknown mechanisms, maybe not until it was too late. And for anything happening beyond our observable universe boundary, definitely not, because no information from those regions can ever reach us. We are watchful, but not omniscient. We observe what we can, analyze what we see, and build models to predict what we cannot see. But there is always the possibility of something unexpected, something beyond our current understanding, happening in the vast regions of space and time that remain hidden from us. The universe is mostly silent. Space is empty, dark, and cold. The signals we receive are faint and require enormous effort to detect and interpret. Most of what happens in the cosmos leaves no trace that we can observe. We see only the brightest events, the strongest signals, the largest structures. Everything else is invisible to us. In that invisibility, in that silence, many things could be happening, and we would not know until the light carrying the information finally completed its journey across the expanding void to reach our tiny planet, orbiting an ordinary star, in an ordinary galaxy, in an ordinary part of space that just happens to be where we are. The paradox of evidence. Now we must confront a philosophical puzzle that sits at the heart of our entire discussion. If the universe is already dead in some regions, what does that even mean for our experience? We exist, we think, we observe. We are clearly experiencing something. Does not our very existence prove that the universe is alive, at least in some meaningful sense? This question requires careful thinking about what we mean by the universe being dead and what relationship our observations have to reality. Let us start with a clear statement. Yes, you exist. Yes, your observations are real. The light reaching your eyes from stars is genuinely light from those stars. The atoms in your body are genuinely atoms. When you observe a galaxy through a telescope, you are seeing real photons that really traveled across space from that real galaxy. None of this is illusion or deception. But here is the crucial distinction. You are observing the past, not the present. The photons you see are real, but they were emitted long ago. They tell you truly what conditions were like when and where they were emitted, but they tell you nothing about current conditions in the place they came from. Think about it this way. Imagine someone dies, but before they die, they record a video message. After they are gone, you find the video and watch it. The person in the video is speaking, moving, alive. The video is real. It truly shows that person as they were. But watching the video does not mean the person is still alive now. The video is evidence of their past life, not their current existence. This is exactly the relationship we have with distant cosmic objects. We see them in our telescopes, alive and active, shining with the light of burning stars. But that light is old. It might be showing us galaxies as they were billions of years ago. Those galaxies might be completely different now. They might have collided with other galaxies and formed new structures. They might have fallen into enormous black holes and been destroyed. They might, in an extreme scenario, have been consumed by false vacuum decay or torn apart by the Big Rip. The light we see is evidence of what they were, not evidence of what they are. So when we ask whether the universe is dead, we need to be very precise about what we mean. We do not mean that the observations are false. We mean that the present state, the state that exists right now in a causally disconnected region, might be lifeless, even though the past state we observe shows life and activity. This creates a strange situation. From our perspective, trapped by the speed of light, the observable universe is the universe. We can only interact with, be influenced by, and observe the region within our light cone. Everything outside that region might as well not exist as far as our direct experience is concerned. It cannot affect us, we cannot affect it, and we cannot see it in its present state. So, in a practical, experiential sense, the universe we inhabit is the universe we observe, which shows life and activity everywhere we look. Stars are burning in the past states we see. Galaxies are rotating and evolving. The cosmic microwave background shows the orderly remnant of the Big Bang. Everything appears healthy and consistent with physical law, but in an objective ontological sense, there might be vast regions of present reality where those conditions no longer hold. Where stars have burned out, where physical laws have changed, where expansion has torn everything apart. These regions exist in reality, but not in our experience. They are real, but inaccessible. This leads to a deep question. Does it matter if regions we can never interact with or observe are different from what we think? If those regions are causally disconnected from us, if they can never influence us or be influenced by us, do they have any relevance to our existence? One answer is no. It does not matter practically. Your life, your experiences, your relationships, everything that is meaningful to you happens within the local region where you can have causal interactions. The present state of a galaxy 10 billion light-years away has no impact on your daily existence. Whether that galaxy is alive or dead or transformed beyond recognition makes no difference to you. But another answer is yes, it matters philosophically and cosmologically. We want to understand reality, not just our local experience of it. We want to know what the universe is actually like in its full extent, not just the bubble we can see. The scientific project is fundamentally about discovering truth, about building accurate models of how things really are. And if vast regions of the universe are in dramatically different states than we think, then our models are incomplete or wrong, and we do not truly understand reality. There is also the question of whether those causally disconnected regions might eventually become causally connected. Remember, the observable universe boundary changes over time. Regions that are currently beyond our light cone will eventually come within it as their light reaches us. If those regions are dead or transformed, we will eventually see evidence of it when the light arrives. And more urgently, if something like false vacuum decay or the Big Rip is happening in currently unobservable regions, it might be spreading toward us. The death might be coming closer. What is currently beyond our sight might eventually reach us and end our existence. In that case, the present state of distant regions is not just philosophically interesting, but existentially important. So the paradox is this. Our observations are real and accurate, showing us a universe full of active galaxies and burning stars. But those observations are of the past. The present might be dramatically different. We cannot say with certainty that the universe is alive everywhere, just because we see life and activity in the past, states that light reveals to us. The evidence we have is genuine evidence of the past, but it is not evidence of the present in distant regions. And the absence of evidence for cosmic death in those regions is not evidence of absence. We simply do not know. This uncertainty is uncomfortable. Humans crave certainty. We want definitive answers. Is the universe alive or dead? Is it safe or in danger? But reality does not always provide the certainty we desire. Sometimes the honest answer is, we do not know, and the structure of space-time prevents us from knowing until information arrives. Living with uncertainty is part of the scientific worldview. We build the best models we can with the evidence available. We make predictions and test them against new observations. We refine our understanding over time. But we also acknowledge the limits of our knowledge and remain open to the possibility that reality is different from what we currently think. The universe might be dead beyond our sight, or it might be thriving. Both possibilities are consistent with our observations. We have reasonable grounds to believe the universe is probably fine based on its past behavior and the consistency of physical law. But we cannot be absolutely certain. And that uncertainty is a fundamental feature of our epistemic situation, not something we can eliminate with better technology or more clever thinking. We observe the past. We inhabit the present. And the relationship between what we observe and what exists is mediated by the finite speed of light, which introduces a gap that cannot be closed. In that gap lies the possibility that reality is not what it seems. Time scales and human perspective. We have spent considerable time exploring terrifying possibilities: heat death, false vacuum decay, the Big Rip, and the fundamental uncertainty created by the speed of light. But now we need to step back and put all of this into perspective. We need to ground these cosmic scenarios in human timescales and ask, how worried should we actually be? The universe has existed for approximately 13.8 billion years. Let me help you understand how long that is. If the entire history of the universe were compressed into a single year, with the Big Bang occurring at midnight on January 1st, then the Earth would not form until September. Dinosaurs would not appear until late December. All of human civilization, from the first cities to the present day, would occupy only the last few seconds before midnight on December 31st. Humans are incredibly new to this universe. Our species, Homo sapiens, has existed for perhaps 300,000 years. That is less than 0.003% of the universe's age. Civilization is only about 10,000 years old. Modern science is only a few centuries old. We have been seriously studying cosmology for less than 100 years. We are babies in cosmic terms. We have observed the universe for an eye blink of its total existence. And yet, in that eye blink, we have learned an extraordinary amount. We have measured the age of the universe, determined its composition, discovered its expansion, mapped its large-scale structure, and understood its evolutionary history back to fractions of a second after the Big Bang. This is a remarkable achievement for such young creatures, but it also means we should maintain humility. We have not been watching long. We have seen only a tiny slice of cosmic time. Long-term processes that play out over millions or billions of years are mostly invisible to us. We see snapshots, not full movies. We measure the current moment and the recent past, but we have no long-term baseline for comparison. Now, let us look at the time scales for the various cosmic death scenarios we have discussed. Heat death, according to current models, is unimaginably far in the future. The last stars will not burn out for trillions of years. Black holes will not evaporate until 10 to the power of 100 years or more have passed. These numbers are so large that they have no intuitive meaning. The universe would need to exist for 10,000 trillion times its current age before heat death becomes a concern. Even if we are wrong about the timeline by a factor of 1,000,000, it is still incomprehensibly far off. False vacuum. Decay is different because it is a quantum probability. It could happen tomorrow, or it could never happen. We cannot predict when a quantum event will occur, only that it might occur with some probability. But the probability appears to be incredibly low. The universe has existed for nearly 14 billion years, and false vacuum decay has not happened in our observable region in all that time. Either our vacuum is stable, not false, or the barrier between the false vacuum and true vacuum is high enough that decay is extraordinarily rare. If we assume the probability is constant over time and uniform over space, we can estimate that the chance of false vacuum decay happening in our region in any given year is vanishingly small. Small enough that it is not worth worrying about compared to countless other risks that have much higher probability. The big ripe depends on the behavior of dark energy, which we are still measuring and studying. Current observations suggest that dark energy's strength is roughly constant, not increasing. If it remains constant, the Big Rip never happens. The universe expands forever, but gravity and other forces continue to work normally on local scales. If dark energy is increasing in strength, calculations suggest the Big Rip might occur tens of billions of years from now. That is several times the current age of the universe. So all three scenarios, to the extent we can predict them, are either extremely far in the future or extremely unlikely. They are not imminent threats. They are long-term theoretical possibilities that emerge from the laws of physics when extrapolated to extreme timescales. For humans, for our civilization, for our planet, these cosmic death scenarios are irrelevant on practical timescales. The Sun will become a red giant and destroy Earth in about 5 billion years, long before any of these universal death scenarios become concerns. And long before that, countless other threats and challenges will face humanity and whatever descendants or successors we might have. Climate change, asteroid impacts, nuclear war, pandemics, artificial intelligence risks, resource depletion. These are near-term challenges that matter on human timescales. They will affect people living now or in the next few generations. Cosmic death scenarios will not affect anyone for billions or trillions of years, if ever. So why have we spent all this time discussing them? Because the question we are exploring is not about practical risk assessment. It is about knowledge and certainty. It is about understanding the limits of what we can know about reality. It is about confronting the strange and unsettling fact that we cannot observe the present state of distant space, only its past. The cosmic death scenarios are useful thought experiments that illustrate this fundamental limitation. They show us that even if the universe were dying beyond our sight, we would not know. Even if catastrophe were spreading toward us, we might not see it coming. The point is not that these things are likely. The point is that they are possible within the laws of physics, and that we cannot rule them out with certainty because of the structure of space-time and the finite speed of light. From a practical standpoint, we should all live our lives assuming the universe is fine. The evidence overwhelmingly suggests it is. The cosmos has been stable for billions of years. Physical laws work consistently. Stars burn predictably. Galaxies evolve along expected paths. Our models are well tested and well confirmed. The probability that something catastrophic is happening beyond our sight is very low. But from a philosophical standpoint, we should acknowledge that we do not and cannot have absolute certainty. There is always a gap between what we observe and what exists. There is always the possibility, however remote, that reality is different from our models. This uncertainty is not a flaw in science, it is a feature of the scientific method. Science does not deal in absolute proof. It deals in evidence, probability, and falsifiability. We build models that explain observations. We test those models against new data. We refine them when they fail. But we never claim to have final, complete, absolute truth. We always remain open to new evidence and new possibilities. The universe might be dead beyond our sight, but probably, almost certainly, it is not. The stars are likely still burning out there. The galaxies are likely still swirling. The cosmos is likely still humming along according to the same laws we see operating everywhere we look. And even if we are wrong, even if some catastrophe is spreading through space toward us, it would not change the fact that here and now, life is real, experiences are meaningful, and we have the extraordinary privilege of being conscious beings who can contemplate the nature of existence. The universe gave us brains capable of asking these questions. That itself is a kind of miracle. Whether the cosmos lives or dies on timescales vastly beyond human experience does not diminish the value of our brief moment of existence within it. What this means for existence. We have journeyed deep into cosmology, physics, and philosophy. We have explored how light creates a barrier between past and present. We have examined the ways the universe could die. We have confronted the fundamental limits on what we can know about distant reality. Now we must ask, what does all of this mean for how we understand existence? The central realization is that we live in a universe where the present is fundamentally local, not global. You can define what is happening right now in your immediate vicinity, but you cannot extend that definition to the entire cosmos in an objective way. The present moment is not a universal fact that all observers share. It is a slice through space-time that depends on your reference frame, your position, your motion. This is deeply strange. It means that the universe does not have a single unified now that exists everywhere simultaneously. It has countless overlapping nows, each one defined from a particular perspective. Your now and the now of someone in a distant galaxy are not the same slice of time. You are experiencing different presents, even though you both exist in the same universe. This fragmentation of the present has profound philosophical implications. It means that questions like, is the universe alive right now, do not have simple yes or no answers. Alive right now, according to whom? From what reference frame? In what causal region? From our perspective here on Earth, the universe we can interact with and observe is the universe within our light cone, the region from which light and other information has had time to reach us. This region shows us the past states of distant objects, all appearing to exist simultaneously, even though they represent different eras. The observable universe is a temporal patchwork, a collage of different moments stitched together by the finite speed of light. The present states of those distant objects lie outside our light cone. They exist, but they are not part of our present. They are in a region of space-time that is causally disconnected from our here and now. We cannot observe them, cannot interact with them, cannot be influenced by them. They might as well be in a separate universe for all the direct contact we have with them. Does this mean they do not matter? That depends on what we mean by matter. Practically no, they do not affect our daily lives. You do not need to know the present state of a galaxy 10 billion light-years away to make decisions, to love people, to pursue goals, to find meaning in your existence. Your life unfolds in a local region where cause and effect operate normally and where you have access to the information relevant to your choices. But intellectually and existentially, those distant regions do matter because they're part of reality. They exist whether we can see them or not. Their present states are facts about the universe, even if those facts are hidden from us. And someday the information from those regions will reach us, and we will learn something about what they were like when the light left them. Moreover, if something catastrophic is happening out there, it might be spreading toward us. The present state of distant space might determine our future. What we cannot see might be approaching. The unknown might become known too late for us to respond. This uncertainty is uncomfortable, but it is also liberating in a strange way. It reminds us that we are not the center of the universe, not privileged observers who have access to absolute truth. We are small, finite beings embedded in a vast cosmos that extends far beyond what we can see or understand. Our knowledge is limited. Our perspective is local. Our certainty is always provisional. And yet, within these limits, we have achieved extraordinary things. We have figured out that the universe is expanding. We have measured cosmic distances that dwarf human comprehension. We have looked back in time to see the universe in its infancy. We have understood the life cycle of stars, the formation of galaxies, the evolution of structure from smooth beginnings. We have built models that explain nearly 14 billion years of cosmic history with remarkable accuracy. This is worth celebrating, even as we acknowledge what we do not know. Science is not diminished by uncertainty. It is strengthened by honesty about uncertainty. Admitting the limits of our knowledge is what allows us to keep pushing those limits outward, to keep discovering new things, to keep refining our understanding. The question of whether the universe is dead beyond our sight is ultimately a question about the relationship between knowledge and reality. We know the past. We observe ancient light. We build models to predict the present. But we cannot observe the present directly in distant regions. There is a gap between our models and reality, a gap that cannot be fully closed because of the fundamental structure of space-time. In that gap, many things are possible. The universe might be exactly as our models predict, or it might be different. We have good reasons to trust our models, but we cannot be absolutely certain. This is the human condition writ large. We make sense of the world with incomplete information, building the best maps we can while acknowledging that the territory always contains surprises. What this means for existence is that we must hold two ideas simultaneously. First, that our observations are real and meaningful, showing us true information about the past and allowing us to build reliable models. Second, that our knowledge is limited and provisional, always subject to revision in light of new evidence, always aware that reality might contain more than we currently understand. This balance between confidence and humility, between knowledge and uncertainty, is the essence of the scientific worldview. We are not paralyzed by what we do not know. We act on what we do know, but we remain open to surprise, ready to update our understanding when reality reveals something new. The universe might be dead beyond our sight, but probably it is not. We exist, we observe, we think, and all of this is real and meaningful regardless of what is happening in causally disconnected regions. The present we inhabit is the present that matters for our lives, even if it is not the only present that exists in the full space-time structure of the cosmos. The gift of delayed information. Throughout this exploration, we have framed the speed of light and the resulting time delay as a limitation, something that prevents us from knowing the present state of distant space. And that is true. It is a limitation. But now I want to offer a different perspective. What if this limitation is also a gift? What if the time delay of light gives us something precious that we would not have otherwise? Think about what the universe would be like if light traveled infinitely fast, if information propagated instantly across any distance. In such a universe, when you looked up at the night sky, you would see every star and galaxy exactly as it exists right now in this present moment. No time delay, no looking into the past, just the current state of the cosmos. At first, this might sound appealing. You would have perfect knowledge of the present state of everything you could observe. no uncertainty, no gap between observation and reality. But consider what you would lose. You would lose the ability to see history. The universe would appear frozen in whatever state it currently exists in, with no access to its past. You could not watch galaxies form and evolve. You could not see stars in different stages of their life cycle. You could not observe the cosmos growing and changing over time. You would see only a single snapshot, the present, with no context for how that present came to be. The speed of light being finite means that looking further into space is the same as looking further into the past. The universe becomes a time machine. Every observation is an archaeological dig, uncovering older and older layers of cosmic history the further we look. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago, when the universe was young and galaxies were still forming from primordial gas clouds. When we observe the cosmic microwave background, we see the universe as it was 380,000 years after the Big Bang, when atoms first formed and light could finally travel freely through space. We are seeing the baby picture of the cosmos. This is extraordinary. We are not trapped in the present. We have access to billions of years of history simply by looking in different directions and at different distances. The universe's story is written in the light traveling through space, and we can read that story if we know how to look. Moreover, the time delay gives us a way to test our models of cosmic evolution. We can observe galaxies at different distances, which means at different points in time, and see how their properties change. We can watch the universe evolve before our eyes, comparing young galaxies to old ones, seeing how star formation rates have changed, tracking how structure has grown from small fluctuations to vast cosmic webs. If light traveled instantly, we would see everything in its current state, but we would have no direct evidence of how it got that way. We could theorize about the past, but we could not observe it. The time delay turns the entire observable universe into an experiment, where we can directly watch the processes we are trying to understand. There is something deeply beautiful about this. The limitation becomes a window. The delay becomes an opportunity. What prevents us from seeing the present gives us access to the past, and the past is where understanding comes from. You cannot understand something fully by observing only its current state. You need to know its history, its trajectory, its evolution. The speed of light provides that history. Consider also that the time delay gives us a sense of connection to the cosmos across vast stretches of time. When you look at a star 400 light-years away, you are seeing light that began its journey in the 1600s. That light has been traveling through space for centuries while human history unfolded on Earth. The light is older than modern science, older than many countries, older than the Industrial Revolution. It is a message from the past, finally arriving at your eyes. This creates a kind of temporal depth to our experience of the universe. We are not isolated in the present moment. We are connected to the deep past through the light we observe. Every photon that enters your eye has a story, a journey, a history. It was emitted by an atom in a star. traveled through the vacuum of space for years or millennia or eons, and finally reached you. You are the end point of that journey, the recipient of that ancient message. There is something humbling and awe-inspiring about this. The universe is not just a spatial expanse. It is a temporal expanse, and we have access to that temporal dimension through observation. We can see the past. We can watch history unfold. We can piece together the story of how the cosmos evolved from a hot, dense, uniform state into the rich, complex, structured universe we inhabit. Yes, this means we cannot know the present state of distant regions. Yes, this creates uncertainty about whether the universe is alive or dead beyond our sight. But it also means we have something rare and precious: access to cosmic memory. The universe remembers its own history through the light still traveling from its past. And we, conscious observers, can receive that memory and understand it. If the universe is dead in some distant regions, we will eventually see the light from that death. It will arrive, and we will learn what happened. The information is not lost forever. It is traveling toward us, and someday it will complete its journey. The time delay means we learn things late, but it also means we learn them eventually. The past is not inaccessible. It is simply delayed. This is the gift of light speed. It gives us history. It gives us context. It gives us a way to observe and understand cosmic evolution across billions of years. It turns the universe into a story we can read, rather than a static image we can only see. So while we must live with uncertainty about the present, we can also appreciate the certainty we have about the past. We know what distant galaxies look like billions of years ago because we can see them. We know how the universe has evolved because we can observe it at different stages. This knowledge is profound and hard-won, and it is only possible because light takes time to travel. The speed of light creates a barrier between us and the present, but it also creates a bridge between us and the past. And in studying the past, we understand the present more deeply, even if we cannot observe it directly. We see where we came from. We understand the processes that shaped our existence. We place ourselves in the context of a universe that is ancient, vast, and ever-changing. This is not just a limitation to accept, it is a gift to cherish. The time delay that prevents us from knowing if the universe is dead right now is the same time delay that allows us to watch the universe being born, growing up, and becoming what we see around us. The same property of light that creates uncertainty also creates understanding. And perhaps that is the most important realization, that uncertainty and understanding are not opposites, but companions. We understand the universe deeply because we acknowledge what we do not know. We make progress because we remain humble about our limitations. We discover truth because we remain open to being surprised. The light traveling through space carries messages from the past, and we are here to receive them, interpret them, and marvel at the story they tell. Embracing cosmic uncertainty. We have traveled far in this exploration. We began by questioning whether the universe might be dead beyond our sight, hidden from us by the time delay of light. We explored the mechanisms of cosmic death. We examined the limits of observation and knowledge. We confronted the uncomfortable truth that we cannot know the present state of distant regions. And now, as we approach the end, we must ask, what have we learned? What does all of this mean? The most important lesson is not about the universe. It is about knowledge itself. We have discovered that there are fundamental limits to what we can know, limits built into the structure of reality. These limits are not technological. We cannot overcome them with better telescopes or more advanced physics. They are woven into the fabric of space-time itself. Light travels at a finite speed. This means information takes time to propagate. This means the present is local, not global. This means distant regions exist in a state that is causally disconnected from our here and now. We cannot observe their present states. We can only observe their pasts and model their presents. This is humbling. For creatures who pride themselves on reason, on science, on the ability to understand nature through observation and logic, it is unsettling to realize that vast portions of reality are fundamentally hidden from us. Not hidden temporarily, but hidden necessarily by the structure of causality. But humility is not weakness. It is wisdom. Acknowledging what we do not know is the first step toward expanding what we do know. Science has progressed not despite uncertainty, but because of it. When we admit ignorance, we create space for discovery. When we question assumptions, we open doors to new understanding. The fact that we cannot know the present state of the entire universe does not make cosmology impossible. It makes it challenging, and challenges drive innovation. We develop new observational techniques. We build more sensitive instruments. We create sophisticated models. We test predictions. We refine theories. We push the boundaries of knowledge outward, even knowing those boundaries can never be completely eliminated. This is the scientific spirit, relentless curiosity combined with intellectual honesty. We want to understand everything, but we acknowledge we cannot. We strive for truth while remaining humble about our limitations. We build maps, knowing they are incomplete, but also knowing they are useful. The question of whether the universe is dead beyond our sight represents the ultimate limit of this scientific project. There are regions whose present states we cannot access. There are questions we cannot answer with certainty. There are possibilities we cannot rule out, and we must make peace with that. Making peace with uncertainty does not mean giving up on knowledge. It means recognizing that knowledge comes in degrees, that certainty is rare, that probability and evidence are what we work with. We do not need absolute proof to act, to decide, to understand. We need good reasons, and good reasons are what science provides. The good reasons we have suggest the universe is probably not dead in distant regions. It has been stable for billions of years. Physical laws work consistently everywhere we observe. Stars follow predictable life cycles. Galaxies evolve along expected paths. There are no mysterious dark zones, no regions where everything has inexplicably failed. The cosmos appears healthy and consistent, but probably not is not the same as definitely not. There is always the slim possibility of surprise. Reality might contain more than our models capture. The universe might be stranger than we imagine, and we will not know until information from distant regions finally arrives. Living with this uncertainty requires a particular mindset. It requires comfort with ambiguity, tolerance for not knowing, willingness to update beliefs when new evidence emerges. These are not natural human traits. We want certainty. We crave definitive answers. Our brains evolved to make quick decisions with limited information, not to carefully weigh probabilities and acknowledge uncertainty. But science asks us to do exactly that, to hold our conclusions lightly, to remain open to new data, to say, "I do not know" without discomfort, to build provisional understanding while acknowledging it might need revision. This is difficult, but it is also liberating. When you let go of the need for absolute certainty, you become free to explore possibilities without fear. You can ask wild questions. You can imagine strange scenarios. You can follow ideas wherever they lead, knowing that even if they turn out to be wrong, the journey of exploration has value. We asked whether the universe is dead. We explored how it could die. We examined why we cannot know for sure. And in doing so, we learned about light, space-time, observation, causality, and the nature of knowledge itself. Even if the answer turns out to be that the universe is fine, and always has been, the question was worth asking because it revealed so much about the structure of reality and our place within it. This is what good questions do. They teach us things regardless of their answers. They force us to think carefully about assumptions we take for granted. They push us to examine the foundations of our understanding. They reveal the complexity hidden beneath simple surfaces. The universe might be dead beyond our sight, or it might be thriving. We do not know with absolute certainty. But we know a lot. We know the history. We know the physical laws. We know the likely future. We have good models and strong evidence. And that is enough to work with. Embracing cosmic uncertainty means accepting that we will never have perfect, complete knowledge of everything. But it also means celebrating how much we have learned despite those limits. Humanity went from thinking Earth was the center of everything to understanding the universe's age, size, composition, and evolution. We went from watching stars without comprehension to calculating their masses, distances, temperatures, and life cycles. We went from terrestrial ignorance to cosmic awareness in just a few centuries. This is extraordinary. And it happened not by pretending we knew everything, but by admitting we knew little and then working relentlessly to learn more. Uncertainty was the beginning, not the end. So, as we contemplate whether the universe is dead, we should feel not despair, but babu. Or that we can even ask such questions. Or that we understand enough physics to explore the possibilities. Or that we have pushed our knowledge to the point where we can recognize its own limits. And or that despite everything we do not know, we have learned so much about the cosmos and our place in it. The universe is vast, ancient, and mostly unknown. We are tiny, young, and limited in what we can observe. But within those limits, we have achieved understanding that would seem like magic to our ancestors. We have turned uncertainty into a tool for discovery rather than a barrier to progress. And perhaps that is the final answer to our question. The universe might be dead beyond our sight, but here, now, in this local region where we exist and observe, the universe is vibrantly alive. Alive with stars and planets, alive with energy and matter, alive with structure and complexity, and alive with conscious beings who can wonder about it all, ask questions, seek answers, and find meaning in the search. That is enough. That is more than enough. That is everything. We have spent hours exploring cosmic scales, billion-year timescales, and universe-spanning uncertainties. We have contemplated the end of everything and the limits of knowledge. But now, in these final moments, we must return to something more immediate and more intimate: your existence here and now. Whatever is happening in distant regions of space that we cannot observe, whatever the present state of the universe beyond our light cone, whatever cosmic death scenarios might or might not be unfolding trillions of miles away, there is one undeniable fact. You are here. You are alive. You are conscious. You are experiencing something. This might seem obvious, but it is actually profound. In a universe governed by physical law, where matter and energy follow mathematical rules, somehow you exist as a being who has subjective experience. You feel emotions, you have thoughts, you perceive colors, sounds, textures, you wonder about existence, you ask questions about reality. This is not something that physics fully explains yet. We understand how neurons fire and how brains process information, but we do not understand how or why that creates the felt experience of being you. This is called the hard problem of consciousness, and it remains one of the deepest mysteries in science. But we do not need to solve that mystery to appreciate its significance. You are conscious. You do experience. And that experience is happening in this place, in this time, in this local region of space-time, where you have causal interactions and immediate awareness. The philosophical uncertainties we have explored, the questions about whether distant regions are alive or dead, the limits on knowledge created by light speed, none of these change the reality of your immediate experience. You are not an illusion. Your thoughts are not false. Your relationships are not meaningless. Your life is not insignificant. The cosmos is vast and ancient, yes. You are small and temporary, yes. But smallness and temporariness do not equal meaninglessness. A candle flame is small and brief, but it is also real. It provides light. It has warmth. It exists genuinely while it burns. You are like that candle flame in the cosmic darkness. You exist for a brief time in a tiny region of an incomprehensibly vast universe. But while you exist, you matter. Your experiences are real. Your choices have consequences. Your existence has value, not because the universe grants it from outside, but because you create it from within through how you live. The uncertainty about distant cosmic regions does not diminish this. Whether galaxies 10 billion light-years away are alive or dead has no bearing on whether your life has meaning. Meaning is local. It emerges from relationships, from purposes, from values, from experiences. It exists in the connections between conscious beings, in the pursuit of goals, in the appreciation of beauty, in the relief of suffering, in the creation of understanding. None of these things require cosmic permanence to be worthwhile. A good conversation has value even though the words fade into silence. A beautiful sunset has value even though it lasts only minutes. Love has value even though people are mortal. The temporary nature of things does not negate their value. It often enhances it, making precious what might otherwise be taken for granted. You live in a universe that allows consciousness to arise. This is remarkable. The physical laws are such that stable atoms can form, which combine into molecules, which organize into cells, which assemble into organisms, which develop nervous systems complex enough to support awareness. This chain of complexity building on complexity is not guaranteed. Many conceivable universes would not allow it, but this one does. And not only does this universe allow consciousness, it allows reflective consciousness. You can think about your own thinking. You can wonder about existence. You can ask whether the universe is dead. You can contemplate your place in the cosmos. You can stand under the night sky and feel awe at the vastness above you, while simultaneously recognizing that you, the observer feeling that awe, are made of the same atoms as the stars you are observing. This is extraordinary. You are the universe becoming aware of itself. When you look at a star, you are not separate from the cosmos, observing it from outside. You are a part of the cosmos, temporarily organized in such a way that you can observe other parts. The iron in your blood was forged in a star that exploded billions of years ago. The calcium in your bones was created in stellar furnaces. You are literally made of stardust, and now that stardust has become conscious and is looking back at its origins. The question of whether the universe is dead in distant regions cannot diminish this miracle. Even if every star beyond our galaxy burned out tomorrow, even if false vacuum decay erased distant space, even if the Big Rip tore everything apart beyond our local group, you would still be here, still conscious, still experiencing, still part of something remarkable. Your life unfolds in the local region where causes and effects are immediate, where your actions have consequences, where you interact with other conscious beings. This is where meaning exists. This is where value is created. This is where your existence matters. Yes, the universe is largely empty space, cold darkness, and dead matter following physical laws. But in tiny pockets, on planetary surfaces orbiting stable stars, complexity has emerged. Life has developed. Consciousness has arisen. And now you exist as one of countless conscious beings scattered through space and time, each experiencing their own local reality, each creating their own meaning. The vast cosmic uncertainties we have explored do not change the fact that here, in your immediate experience, things are real and they matter. Your relationships with friends and family are real. Your pursuit of goals and dreams is real. Your experience of joy, sorrow, curiosity and wonder is real. The love you give and receive is real. The understanding you build is real. The kindness you show is real. These things exist in the local region of spacetime where you have causal influence. They do not require the entire universe to be alive. They do not require perfect knowledge of distant regions. They do not require cosmic permanence. They require only that you exist here and now and engage with the reality around you. So while we can wonder about the state of the universe beyond our sight, while we can explore the limits of knowledge and contemplate cosmic death, we should not let these vast abstractions distract us from the concrete reality of our immediate existence. The here and now is where life happens. It is where meaning is made. It is where you matter. Whatever is happening in the distant cosmos, whatever we cannot know about regions beyond our light cone, whatever the ultimate fate of everything might be, there is no escaping this simple truth. Right now, you're alive. Right now, you're part of something remarkable. Right now, you have the opportunity to experience, to choose, to create, to connect, to understand. That is not diminished by cosmic uncertainty. That is not negated by vast scales. That is not made meaningless by eventual endings. That is the gift of existence, and it is yours to have and to hold for as long as you live. The universe might be dead beyond our sight. But here, where you are, it is vibrantly alive. And you are part of that life, experiencing it, contributing to it, creating meaning within it. That is everything that matters. We close where we began, looking up at the night sky. The stars you see are ancient light, messages from the past, echoes of how things were. Some of those stars might be dead now. Some of those galaxies might have changed beyond recognition. The present state of distant space is hidden from you by the fundamental structure of reality. But as you stand there looking up, something remarkable is happening. Light that has traveled for years, for centuries, for millions of years, is ending its journey in your eyes. Photons that began their voyage when dinosaurs walked the earth, when your ancestors were learning to use fire, when the universe was young, are finally arriving at your retina, being absorbed by molecules, triggering electrical signals that your brain interprets as the sight of stars. You are the endpoint of these ancient journeys. You are the receiver of cosmic messages. You are a witness to the universe's past, and through you, that past becomes present again, remembered, appreciated, understood. Whether the universe is alive or dead in its distant reaches, whether our knowledge is complete or limited, whether certainty is possible or forever beyond our grasp, this moment of looking up at stars is real. The wonder you feel is real. The curiosity that drove you to ask whether the universe is dead is real. The consciousness experiencing all of this is real. The universe created you. It organized matter and energy in such a way that you could arise, think, wonder, and ask questions about existence itself. It gave you a brief window of awareness, a moment in cosmic time when you can look around and marvel at it all. This might be a rare thing in the cosmos. Consciousness might be incredibly uncommon, arising only in tiny pockets scattered across vast expanses of empty space. Or it might be common, with countless beings throughout the universe looking up at their own skies and wondering the same questions you are wondering. We do not know. we might never know. But what we do know is that it happened here. It happened in you. Against all odds, in a universe that could have been lifeless and dark, consciousness emerged, and you exist. The speed of light prevents you from knowing the present state of distant space. But it also connects you to the past of that space, giving you access to history, allowing you to see the universe's story unfolding across time. The same property that limits knowledge also grants understanding. The universe might be dead somewhere beyond your sight, but it might also be thriving, filled with stars and galaxies and perhaps other conscious beings asking their own questions about existence. You cannot know for certain. But the honest answer, based on all the evidence, based on the consistency of physical law, based on billions of years of stable cosmic evolution, is that the universe is probably fine. The stars are probably still burning. The galaxies are probably still turning. The cosmos is probably still doing what it has been doing for nearly 14 billion years. And even if you are wrong, even if something unexpected is happening beyond your sight, it does not change the fact that you are here, now, part of something remarkable, experiencing the gift of consciousness in a universe that allows such things to exist. So look up at those stars. Know that you are seeing the past. Accept that you cannot see the present. Embrace the uncertainty. Feel the wonder. And appreciate that you, a temporary pattern of matter and energy, get to participate in this grand cosmic story. The universe might be already dead beyond your sight. But here, where you stand, where you think, where you wonder, where you live, the universe is vibrantly, undeniably, beautifully alive. And so are you. And that is the only certainty you really need.